You've just finished pouring a perfect concrete slab. The finish is smooth, the weather is decent, and you're on schedule. The foreman suggests pulling a crew off to start on the next task, saying the concrete will harden on its own. This is the moment, the decision that will determine whether that slab becomes a durable, strong, long-lasting part of the structure or a weak, cracked, and costly liability. The single most important thing you can do for concrete after you place it is to cure it. And yet, it's the step most often rushed, ignored, or misunderstood. In this video, we're going to eliminate all confusion. I'm going to show you not just how to cure concrete, but why it's non-negotiable. We'll look at the dramatic science behind it, the shocking numbers that prove its importance, and the simple site practices that separate professional results from amateur failures. To understand why we cure, we need to start at the microscopic level with a chemical reaction that gives concrete its strength: hydration. Hydration is the process where cement particles react with water to form a complex, interlocking matrix of crystals. This crystal matrix is what binds the sand and aggregate together, creating the hard, strong material we know as concrete. This is the most critical concept. Concrete does not dry to get hard. It undergoes a chemical reaction that requires water. If water is present, the reaction continues, and the crystals continue to grow and strengthen, filling in voids and creating a denser, more impermeable structure. If water is removed, the reaction stops. It's that simple. Curing is the process of maintaining a sufficient amount of water and a favorable temperature within the concrete to allow this hydration reaction to continue for as long as possible. You are not just keeping it wet, you are actively feeding the chemical reaction that builds strength. So, what happens if you don't cure the concrete? The consequences are severe and permanent. The most immediate danger is plastic shrinkage cracking. This occurs in the first few hours after placement, while the concrete is still fresh. If the surface loses water faster than it can be replaced by bleeding, which happens on hot, sunny, or windy days, the surface layer dries out and shrinks. Since the underlying concrete is still plastic, this shrinking surface layer tears itself apart, creating a network of fine cracks. Once these cracks form, they are permanent. They become entry points for water and chemicals that will accelerate the deterioration of the slab. But the problems don't stop there. If hydration stops prematurely due to a lack of water, the concrete will never achieve its potential strength. The concrete surface, in particular, becomes weak, dusty, and prone to abrasion. This is because the surface is the most vulnerable to water loss. A poorly cured surface will have a low cementitious paste density, meaning it can easily wear away, a problem known as dusting. Now let's talk numbers, because the data behind curing is staggering and should be a wake-up call for any project manager focused on quality. A classic study and countless field observations have proven that properly cured concrete can be more than 50% stronger than identical uncured concrete after 28 days. Think about that. You're using the exact same mix design, the same cement, the same labor, but by simply adding water and protecting it for a few days, you get a material that is twice as strong. The difference is most pronounced in the early stages. After just 3 days, properly cured concrete can already be over 100% stronger than its uncured counterpart. This has direct implications for safety and scheduling. For example, if you're planning to remove forms or reshore based on a specific concrete strength, improper curing means you'll be waiting longer, or worse, you'll be applying loads to a concrete that is far weaker than you calculated. Furthermore, proper curing dramatically reduces the concrete's permeability. A well-hydrated paste has fewer and smaller capillary pores, making it much more resistant to the penetration of water, chlorides from de-icing salts, and sulfates from the soil. This is the key to durability, especially for structures like parking decks, bridges, and marine facilities. So, how do we actually cure concrete? The goal is always the same: prevent moisture loss. The methods vary based on the application and site conditions. The most effective method is water curing. This involves continuously ponding the surface with water or using saturated burlap or cotton mats to keep the surface wet. This is considered the gold standard because it positively adds water to the mix. However, it's labor-intensive and not always practical. The second most common method is using a liquid membrane-forming curing compound. These are sprays that form a thin, continuous film on the concrete surface, sealing in the moisture. They are incredibly efficient for large areas like slabs and pavements. A critical pro tip for materials engineers: Always ensure the membrane is applied immediately after the final set and the sheen has disappeared, and that it forms a continuous, unbroken film. A patchy application is worse than useless. The third category is covering the concrete with water-retaining materials like damp sand or straw, or using impervious sheets like plastic. Plastic sheeting is very effective but must be sealed at the edges and can sometimes discolor the concrete if it touches the surface unevenly. The choice of method depends on the element. A vertical column requires a different approach than a horizontal slab, the available resources, and the weather. Finally, let's talk about timing and duration. When should you start curing? The answer is as soon as the concrete has hardened enough to resist surface damage. For flat work, this is typically immediately after the final finish has been applied and the bleed water has evaporated. You cannot wait until the next day. By then, immense amounts of moisture have already been lost, and plastic shrinkage cracks may have already formed. For vertical elements, you often need to wait until the forms are removed, but then curing should begin immediately. How long should you cure? The American Concrete Institute, ACI, recommends a minimum curing period of 7 days for concrete reaching 70% of its specified strength, and longer for concrete with supplementary cementitious materials like fly ash or slag, which hydrate more slowly. A best practice is to always cure for at least 7 days, and to maintain the concrete temperature above 50 degrees Fahrenheit to ensure the hydration reaction proceeds at a reasonable rate. In extreme weather, your curing strategy becomes even more critical. In hot weather, you're fighting rapid evaporation, so you might need to combine wet curing with windbreaks or sunshades. In cold weather, you're not just retaining moisture, you're also providing insulation to ensure the concrete doesn't freeze and that the hydration heat is retained, which is a topic we can cover in a future deep dive video. In conclusion, curing concrete is not a passive waiting game. It is an active, intentional process of creating the ideal environment for strength and durability to develop. It is the cheapest and most effective insurance policy you can buy for your concrete structure. The small investment in time, labor, and materials for proper curing pays for itself 100 times over in avoided repairs, increased service life, and guaranteed structural performance. You wouldn't stop feeding a baby before it's grown. Don't stop feeding your concrete the water it needs to reach its full potential. Now I have a question for you. What is the biggest challenge you face with curing on your projects? Is it convincing management to allocate the time or dealing with difficult weather conditions? Let me know in the comments below. If this breakdown of concrete curing was valuable, please give this video a like and subscribe to the channel for more content that helps you build better.